So now that we've talked about velocity and speed, basically just talking about how fast things can move, we now need to apply that to when speed changes. And this is known as acceleration. So there are a few more things that we need to understand about how objects can accelerate and how we can calculate that. The definition of acceleration is the rate at which an object changes its velocity. So an object is accelerating if the velocity is changing in any way. So we learned in our notes about speed and velocity that velocity has to do with how fast an object's going, but it also has to do with its direction. So velocity can change by either increasing speed, it could decrease speed. Another word for that is called deceleration. And another way velocity could change is by changing the direction. So even if the speed doesn't change, if the object's direction changes, so say a car is going like 70 miles an hour on the bypass and it turns on the bypass because the road curves. Because it's doing that, it's technically accelerating. So the formula that we need to write down in our notes is that acceleration is equal to the final velocity, so the velocity at the end. Subtracting from that is the initial velocity, and when you figure out the difference between those two, you divide it all by the time. So yesterday we talked about how our unit for velocity is meters per second, and our typical unit for time is seconds. So when we have our unit for acceleration, if we were to write it all out, it would look like this, which is super confusing because it involves two division symbols. So instead what we're going to say is acceleration is equal to meters per second squared. So this little 2 here should actually be smaller. So when we talked about acceleration due to gravity, if you were to fall out of a plane, and we said that you would fall at 9.8 meters per second squared, that's all relating back to acceleration. So you've already been exposed a little bit to this unit, but we just need to remember that's what we're going to use when we're dealing with acceleration. So we have some practice problems here dealing with these data tables, and we're just going to assume that a car has been traveling for a certain amount of seconds, and as it's starting in this first table, we see that at the very beginning the velocity is 0, which means the car is sitting still, and after 4 seconds the velocity has gone up to 8. So I'm going to work these problems out with you right now, and I'm going to show you how we can abbreviate these different terms so that way you're not having to write out the whole words, initial velocity and final velocity. So velocity is a V, and you're going to put a little f next to it like a subscript. And then we'll put a V with a small I next to it, and we'll put that all over T. Okay? That doesn't look a T. So I'm going to have my final velocity equal 8. And your initial velocity is 0. And you have to look at how much time it took to do that. So it took 4 seconds overall to complete that part of the data table. So 8 minus 0 is 8. You're not taking anything away. And then you're dividing 8 by 4. So your acceleration for this car was 2 meters per second squared. So it's saying every second this velocity changed, or it went up by 2 meters per second. You can see that in the data table. Now let's try this other one, this other practice problem right next to it. Again, we'll start out writing our formula. Velocity final minus the initial all over time. Okay, and I'm writing this condensed so it takes up less room, but if you want to use each row kind of like what we've done in the past, you can do that too. So again, we're looking at our final. So after the 4 seconds has taken place, our velocity is at 0. So you need to think to yourself, what does that mean if after 4 seconds my velocity has gone down to 0? That tells you that this car has gone to a stop. So it's most likely slowed down because the initial velocity was 8. So after we've gotten up to 8 in the first practice problem, the second one, we're now going back to a stop. So now we've got 0 minus 8. And again, it took 4 minutes overall, or I keep saying minutes, 4 seconds overall to do that. So now 0 minus 8, if I take 8 away from 0, that means I have negative 8. And I'm dividing that by 4. So when I have a negative involved, that means I have negative 2 meters per second squared. This negative tells me that instead of speeding up, I'm actually slowing down. Okay? So every second that passes, you can see that it goes down by 2 meters per second. So that's where we get this number from. So if you were to have constant acceleration, kind of like what we talked about with constant velocity, the word constant means same. So if I have constant acceleration, that means that velocity is changing by the same amount each second that passes. So if I were to put this on a graph that deals with velocity on the y-axis and time on the x-axis, I'm going to have a steady slope that doesn't curve, it doesn't kind of break and do like different shapes or anything. It is one solid line because it is constantly changing by the same rate. Now if I have a constant velocity and I were to plot this on a graph, I don't really plot direction on the graph, but if I were to plot velocity versus time again, and it is not changing its speed at any rate, you can see in this picture, every second it has gone forward the same amount of distance, so that means the velocity isn't changing. So that means that this line here is level with the ground, it's horizontal, because my velocity is starting at 10, and every second that passes, it's still 10 meters per second. So it doesn't go up or down, it just goes straight across. Now if the velocity were to change, that's when we would see it go up or down on the graph. Now if we put acceleration on a graph that has to do with distance or position divided by time, we would see a curve. So hopefully you can notice that after 1 second, it's just gone a little bit of distance. And every second after that, the distance increases more and more. So this is like being at a stoplight and the light turning green and a person accelerating or stepping on the gas to increase their distance more and more to get up to the speed they want to go on. So if we were to plot that information on a graph, they would end up having a curve. So when we're reading graphs, we have to be really careful to pay attention to what the axes mean. Most of the time you're going to see time on the x-axis, but the big important thing here to look at is what's on the y-axis. So if I were to have velocity and time on a graph, if the line is moving up, that means my velocity is increasing with time. So that means I'm accelerating. Now as the line kind of levels out, that means I've hit cruise control. So you can imagine somebody driving and increasing their speed until they get to a certain speed and they want to stay that same velocity, so that way they don't have to like keep pushing their gas pedal, so they can put it in cruise control, and that's when we have this horizontal line. Then when the line goes back down, that's decreasing the speed, so that's called decelerating. Now if we look at the same shape of this graph but put it over here on this graph, you need to pay attention. This is distance. So now this means that I am leaving point A and I'm getting a certain distance away from this point. So say I'm at home and I realize that I don't have everything I need for dinner, so I need to go to the grocery store. So I drive away from my house, I get to the grocery store, and this part of the line, when it's level, means that the distance is not changing for that entire amount of time. So that means I must have parked in the parking lot and gone in the grocery store and bought the things I needed. And now as the line goes back down towards the x-axis again, this means that I'm kind of doubling back, or I'm covering the same distance that I did before, and I'm going back home. So hopefully you can understand, even though these two graphs have the same shape, this little almost like a trapezoid without the bottom, because they're on different types of graphs, they mean different things. So if you have questions about looking at graphs, please make sure that you write down these questions so we can talk about them in class. We'll have some more practice with this tomorrow. And if you need some help in figuring out how to solve the practice problems at the end of these notes, be sure to watch the next video and you'll be able to go through the problems with me, or even just check your work to make sure that you did it correctly.